Check this out. We've got something really fun today. This is so amazing. Oh man, again? 1.5 Infinite Geometric Series. This is a geometric series that goes on forever and ever, which is pretty wild to think about. Let's try these two examples here and see if they add up to anything particular. So in this one, 1 plus 4 plus 16 plus 64 plus 128 and so on. If we keep adding this up, we never find a value that it rests on or gets close to, and this we would just say approaches, like gets closer and closer to infinity. The next one here, we've got 2 plus 1 plus a half plus a quarter, and if you tried this, keep adding more and more values in this series, then we find that this one approaches 4. It gets closer and closer to 4. Now we can see this visually by looking at a ruler here. If we add 2, so starting from 0 here, and we add 2, so this is how far we are. Then we add half of that, so we add 1, okay? And then we add half of that again, so a half. Then we add half of that, so a quarter. Then we add half of that, so an eighth. Then we add half of that, so a 16th. Then we add half of that, and so on. And we just keep getting halves and halves, and we get closer and closer to this value of 4. A convergent series is a series with infinite number of terms in which the sequence of the partial sums approaches a fixed value. So for example, this one right here, we've got 4 plus 2 plus 1. Our S1 here would just be 4. Our S2 would be 6. Our S3, 7. Our S4, 7.5. And our S5, 7.75, and so this sequence right here is getting closer and closer to a specific number. Let's actually try graphing this in our calculators to see if it does really approach a certain number. So our T1 here is 4, and we have 1 minus the R value, the common ratio, and that would be a half, or 0.5, to the power of n. In our calculator, we're going to make that x. And then in the denominator, 1 minus 0.5. Now we can simplify this because 1 minus 0.5 is just 0.5. If we're dividing by 0.5, that's like multiplying by 2. So this can be written as 8 times 1 minus 0.5 to the power of n. Now let's actually see what that would look in our calculators. So bringing that out here, that's what we'd graph, and this is what the graph looks like. So you can see that the graph starts to get very steep here at the beginning and then levels off, and we're adding less and less. So it's as if there is a horizontal asymptote here that we are snuggling up next to. So let's use the table of values and see if indeed we get closer and closer to this value here, and what is that value. So S7 is something like 7.9375. S11 is 7.9961. And S17, we get to 7.9999389648. Okay, something like that. So you can see that the further we go, the closer and closer we are getting to 8. So that's what the partial sums is. This would be a partial sum because it's not the sum of the whole series, it's just a partial sum of it. And it's getting closer and closer to 8. So as our term number approaches infinity, then the sum of this series approaches or gets closer and closer to 8. Never really touches 8, but for our purposes, we say that the infinite sum is equal to 8. So we kind of cheat here and we say if we could get to infinity, then this would finally get to 8. A divergent series, on the other hand, is a series with infinite number of terms, and this sequence does not approach a fixed value. So for example, this, we would have S1 here is 4, S2 would be 12, S3 would be 28, and S4 would be 60. So you can see that this is just getting larger and larger. Let's try graphing this on the calculator and see what it looks like. So our term 1 is 4. We've got 1 minus. This time our R value is 2. We're doubling each time to the power of n. And in the denominator here we have 1 minus 2. And so we can also simplify this. If this is 1 minus 2, this is just negative 1. So I'll just move it up to the numerator here and graph that. And that looks like this, where you see that this graph just skyrockets off. There's no horizontal asymptote. It does not get closer and closer to a specific value. Let's look at the table of values then and find these sums here. S7 is 508. S11 is 8,188. And S17 is 524,284. This is definitely not going to a specific value. So therefore, its sum cannot be calculated. Just goes off and approaches infinity as n approaches infinity. We need to figure out when a series converges and when it diverges. If it diverges, then the sum is infinite. We can't calculate it. We're not really interested in those. We're interested in which ones converge, and therefore which ones can we find the infinite sum for. So 1 plus 3 plus 9, this one, if you graph it or if you try to add this up, it diverges. And the R value here is 3. Let's look at the next one. This one alternates, so it's pretty interesting. Negative 1 plus 2 minus 4 plus 8 minus 16, and so on. This one we find also diverges, and the common ratio here is negative 2. So it doesn't matter if it's negative or positive. Okay, let's look at some other examples. So 5 plus 1 plus 1/5. So this one is, the R value is 1/5. And this one converges. So it approaches, looks like 6.25. This one here, our R value is negative 1/2. And we try to add this one up, and we find that it converges as well. So it approaches 4. So which ones converge and which one diverges? Looks like if the absolute value of R is in between 0 and 1, then we're going to converge. What happens to the formula for infinite geometric series? Again, if the series diverges, then we don't really care. There's no formula for that. But if the series converges, we need some calculus, and then we can simplify this formula. What happens to R to the power of n when n approaches infinity and R, the absolute value of R, is in between 0 and 1? Let's do a simple example. So if we had, say, R is equal to 1/2, and then we had R to the power of n, and n approaches infinity. So we would say that the limit, and you don't need to know this notation until calculus, but we have the limit as n is going to infinity of 1/2 to the power of n. That means that we're going to multiply this out forever and ever, which we can't do. And that's why we need this little calculus sign here. This is our way that we can get around the impossible. So if we were to multiply this out and keep going forever, we can imagine what happens to this value, or we can figure out what value it's going to get really, really close to. So let's see, if we have the numerators multiplying together, 1 times 1 times 1, as many times as we want, is just going to equal 1. But what about 2 times 2 times 2 times 2 times 2, forever and ever? This value is going to get larger and larger, and so as n approaches infinity, this denominator here also approaches infinity. And I put it in quotation marks here because we can't actually have infinity. It's not a number here, it's just a concept. Now think of this, if you had one cookie and you're going to divide it among everybody in the world, that's not even infinite. You can see that you're really not getting any of that cookie. Now imagine having one cookie and dividing it among all the planets and all the stars in the universe and all the aliens and humans. And now you really aren't getting any of that cookie. So really, this, for all intents and purposes, just gets closer and closer to 0. So we can say that the limit is 0. So that's the concept we're going to use to simplify this formula right here. This part of the formula, since the absolute value of r is in between 0 and 1, we multiply it more and more times, and it goes to 0. So we cease caring about it. And so that's gone. So all we're left with is term 1 times negative 1, and in the denominator, r minus 1. Now it's awkward to have a negative 1 in the numerator here, so let's multiply numerator and denominator by negative 1. This would give us term 1 over, and all we're going to do is flip this around, 1 minus r. And that is our new formula for infinite geometric series that converges. Let's see how that works with these examples. So we've got this sequence here. We want to determine the infinite sum. So our first term here is 120. Our ratio is 1/2. So that's good because it's in between 0 and 1. So we can do our infinite sum, and that will equal T1 over 1 minus r. So our first term is 120. 1 minus 1/2, that's 120 over 1/2, which is the same as 120 times 2, so that infinite sum is 240. Let's do the next one. So our infinite sum is our first term here, and now our common ratio is negative, so our ratio here is negative 2/3 divided by the previous term here, which is 2, and so our common ratio is negative 1/3. So in the denominator here, 1 minus negative 1/3. So we have 2 in the numerator. This would be adding here, so 1 plus 1/3, which would be 4/3. And if we're dividing, dividing by a fraction, we can multiply by the reciprocal, so 3 over 4. And simplify this or multiply it through, and we can get that this is 3 over 2, or if you want, 1.5. Determine the sum of this infinite geometric series. So for this one, our first term is 9, and looks like our common ratio here is 0.1 or 1/10. So 9, and in the denominator, 1 minus 1/10. And we can do 1 minus 1/10 is 9/10, and we multiply and calculate this, and it equals 10. Next one, determine the sum of this infinite geometric series. So we've got S infinity is equal to, the first term is 5 over 1 minus the common ratio. So it looks like the common ratio here is 3 over 2. And we can calculate this. It's 5 over negative 1/2, and this equals negative 10. Now hopefully some of you are wondering what I'm doing, because this has a ratio of 3 over 2. So this one diverges. And so no sum. Watch out, because if you try this formula on a series that diverges, you still get an answer. So of course it's not negative 10. If you observe here, we're adding up a bunch of positive numbers. Couldn't possibly equal negative 10. But this formula still produces an answer. So be careful. Always check the common ratio that its absolute value is in between 0 and 1. We can also use this infinite geometric series to turn a repeating decimal into a fraction. So if we have a repeating decimal, it just keeps repeating. It might repeat only 2, or in this case, 3 digits, or maybe just 1 digit. We can break it up. So each 3 digit will give its own term. And you can see there's a pattern here. Every time we multiply by 1/1000. So let's determine the sum of this series. So our first term here is 0.584. And our R value here is 0.001. So our infinite sum is going to be 0.584 over 1 minus 0.001. Now, probably fractions are easier to deal with here, so I'll write this as a fraction 584 over 1,000 divided by 999 over 1,000. And that way the thousands can cancel out, and I'm just left with 584 over 999. This was part of Relations and Functions 10, analyzing geometric series. Here's some questions from the textbook. Give them a try. See if you know what you are doing.